So the thing is that I don't know actually know a good website that explains this. So I will briefly talk about how to do solid of revolution. And basically, it's about when you have a curve. When you have a curve like this, when you rotate it along an axis, and it gets to some three-dimensional thing, which is like an outer shell of something, and there is a volume under that thing, which you can integrate. Without two-dimensional integration, you can only use one-dimensional integration to do that. Which, suppose you rotate this line, you can imagine that you get something like an empty bowl, an upside-down empty bowl, which is like this. And what you want to do is basically find the volume under this thing, under this surface. So there are basically two ways of doing it. And the first way is called the disk method or the washer. I will call it disk. So the way to think about this, because you want to find the volume of this mountain thingy, what you want to do is you want to cut it into small disks. So if you cut it along this line, then you basically get a small disk like this. And if you cut along another line, you will get a small disk. And the disk should not be flat, it should have some kind of height, and we call that height dy. So if we look at this thing from the front, it has this shape, and when we cut into small disks, you can imagine we are cutting like this. And imagine you have a mountain and you do this kind of cuts, then each one piece of the mountain will be a circle. I mean, not a circle, a disk. A disk with circle on the top, no matter what the shape of mountain is, because this is very small, so the edge of this thing is, it could be curvy, but we assume it's like straight. So, but then the disk will have different radius, and the radius is basically changing when Fy is changing, when the function is changing. So we call this radius F of y, and the radius basically changes as y changes and as Fy changes. And the volume, the way to calculate the total volume is sum up the volume of these small disks, and then take the limit as the disk height or the disk thickness go to 0. So the volume of each one is just pi r squared, because the area of the circle is pi r squared, and you multiply by the height. And then you take the limit as y goes to 0 of the sum of all these disks. And then by definition, this limit of sum will be an integral. That's the first method. And the second method is the shell method, which is a lot harder to understand. So suppose you still have the same mountain, and you want to take it out layer by layer. So suppose you take out one layer like this. So a layer will be very thin, so you cut it out like this, and you basically cut it out until nothing is left. So if you view the mountain from the top, so this time you view it from the top, then it looks like just a circle because it's a mountain, so from the top it's like this. And the way you cut it is ring by ring. So you just imagine you have a mountain and you cut it like this, then each ring would be something like a shell, so it would be something like this. So we're basically taking this mountain out layer by layer. And each layer has a small volume, and then we add them up. So the volume, note that this radius is no longer changing because of the function. It's just because the distance from the base, the center of this mountain is changing. So this radius is just x. But the height of this thing is changing because of the shape of the mountain. So if the mountain shape is different, then, so suppose it's like this, then the height of the shell is changing according to the height of the function. But the radius is always just x, so that's why we call this thing x, and the height f of x. And the volume of each small thing is approximate. Note that here is approximation, so it's not exact, but you can approximate it. by the surface area multiplied by the thickness. Remember, dx is the thickness of each shell. So a way to think about this is, suppose you cut it and then you flatten it, then it becomes something like this very flat thingy, which has thickness dx, and this length is obviously the circumference of the circle, and the circumference is 2 pi r. The r here is x, and remember there's a height, so the height is f of x, so 2 pi x f of x dx would be the volume of each shell. So after you have each shell, then you basically, what you do is sum them up again. So the limit as the shell thickness goes to 0 of the sum of all the shells, which is from 0 to a, and by definition will just be another integral. So another two type of things that you might see is, first, suppose the mountain is not really a mountain, it's something like a volcano which does not have anything in the middle, so here is empty. So suppose you have that, and then the shell would not be starting from 0, would be starting the innermost shell. So the smallest really such shell is basically something like this. And the shell basically increase by size, so at here is the highest shell, which I cannot really draw, but it's something like this, and it basically decrease. Here there's a very flat shell, which this drawing makes it even uglier, so I will not do it. So when you sum up these shells, you are integrating from A to B, and A is the innermost shell you have, and B is the outermost shell. So again, you are cutting this, like, suppose you view this from the top, it's the volcano thing here in the middle is nothing, and until here is A, here is B. So the way you cut it is cutting round and round. So each ring is basically a very thin shell, and then you sum them up, but you sum them up in a way such that it's from A to B, not from 0 to B like before. And the formula is the same. So this is the surface area multiplied by the thickness. Similarly, there's the same situation for disks. So go back to this volcano. There's no way of reintegrating this with the disk method, because no matter how you can think, like, no matter how you cut it, none of it's really a disk with a function on the outside. So if you cut it like on top to make a disk, it doesn't really work because both sides are functions, so you cannot do anything with it. So that's why there are some cases where only shell can be used, for example, this volcano case. And similarly, there is something that only disk can work. So suppose you are cutting out shells, then there's no way of cutting in with the function tree, because the shell would be like piece by piece, so there's no way of defining what function it is we are integrating. So in this case, we can only use disk. So suppose you are cutting this thing up, so suppose you look along the side, then from one side it's looking like this, so you cut the disk out like this. So the drawing is very bad. It's even worse than the original one. But anyways, so each piece will be a disk like this, but the middle of the disk is empty. So the way to deal with this, suppose you have a disk like this. So the way to find each element or each unit volume is very easy, because it's just the big R squared minus the small r squared multiplied by pi and multiplied by the thickness would be the volume of each piece, and then you sum them up. So integral, again, pi of big R squared minus small r squared. So the outside radius minus the inside radius multiplied by the thickness, and you sum them up. So these are two special cases which you can use only one of them, but the other one does not work because the function, because of the difficulty in defining the top and bottom function. And there is one very simple example, which is just integrating the volume of a sphere, which you should probably know already. The volume of a sphere is this r cubed pi. So we'll try to use integration to find that. So So the first way to do it is by cutting this thing up into disks, which you can probably imagine it by cutting a sphere into pieces of disk, which is very easy to visualize. And the way I do it is I cut it into half first. The other half will be the same, so I'll use 2 times that half. So starting from radius 0 on the top to radius of r, I add up the volumes of these disks. So each disk is defined by the outer function. So the function here is in terms of y. So you should know that the function for a circle is x squared plus y squared is equal to r squared. So if you invert it, you get the square root of r squared minus x squared as a function of y. So when you integrate this, you get pi r squared multiplied by dx as each volume of each disk, and then you do the integral. So integrating from radius 0 to radius r, and you integrate this thing. And this integration, I believe, is very easy because the square root and the square cancels out. So you just are integrating a polynomial, and this is 2 times this, and you get this answer, which is what you should have. The way to do it with shell is a lot more difficult, but the idea is very simple. So suppose I'm only integrating the top half of the sphere, so it's a half sphere, and I'm cutting it up like shell by shell. So the thing we are integrating is, of course, from 0 to r, because the radius of the shell is smallest radius is 0 because it's very thin shell, and the largest one is the very flat one at r. So we are just integrating those things, and the formula is exactly the same because we are integrating the same thing, but this time is, remember, 2 pi x multiplied by fx is the volume of each shell, and we integrate them up, and remember, so multiply by 2 because I cut it into half in the beginning. So the way to integrate this is using substitution. So suppose we have this thing, u is equal to r squared minus x squared, then du is basically minus 2x. So we have square root u du then. And then when we are integrating this, we get the integral of square root is 1 over 2 square root u. So that's actually wrong. I'm sorry. So the integral of square root of u is the integral of u to half. So it's actually u to the power 3 over 2 and multiplied by the reverse, so it's 2 over 3. So that is the correct formula, and you substitute back u as this thing. So it's 2/3 square root of r squared minus x squared. I'm sorry, there is no square root here because, yes. So it's r squared minus x squared to the power 3 over 2, 3 halves. Because the u is just r squared minus x squared, there's no square root here, so when I substitute back, it should be the original one. And again, this is a polynomial. And when we integrate it, we get the same number. So it shows that both the shell method and the disk method gets to the same answer, and that answer is what we usually believe to be the volume of the sphere.